Hi there, in this video I'm going to show you how to differentiate natural logarithmic functions. So let me title this Derivative for natural logarithmic functions. So we're going to look at the derivatives for ln, okay? So let me take a red pen and a ruler, underline this. So first of all, let me give you the standard result for when we differentiate y equals ln x. So here's the standard result. So if y is equal to ln x, so we call ln the natural logarithmic function, dy over dx, so when you differentiate ln x, you should get 1 over x. Okay, so that is the derivative for the natural logarithmic function ln. Okay, so let me highlight this result. Let me give you an additional result which is based on this result. So let me title this additional result. Okay, so this result is based on the standard result that I've given. So if y equals a ln ux, so in this result a is a constant and ux is any function of x. So where a is a constant and ux is a function of x. Okay, so let's find the derivative of such a function using the chain rule. Okay, so let's use the chain rule in order to find the derivative of this function. So remember, in this function a is a constant and ux, this term here, is a function of x. So let's use the chain rule. So in step number 1, by chain rule, so remember the chain rule, to calculate the gradient function dy over dx, dy over dx is dy by du multiplied by du over dx. Okay? Now, in the second step, so I'll call this step number 2, let's work out dy over du of this function y equals a ln ux. So let me do that as a side calculation. So y is a ln u, okay? So my u is the shorthand for ux. And let's find dy by du. So let's differentiate this with respect to u. Now, bearing in mind a is a constant, based on the standard result for the derivative of ln, when I differentiate ln x, it's 1 over x. So therefore, if I differentiate a ln u, a is a constant, the result is going to be a over u. Okay? So that is dy by du. And in the final step, step number 3, if I replace dy by du by the term that we found, therefore dy over dx, that is dy by du, which is a over u, multiplied by du over dx. So this is the result here for the derivative of y equals a ln ux, where a is a constant, ux is a function of x. Okay? So you can only use this result here if a is a constant, remember, and ux is a function of x. Now, don't memorize this result here, just learn and appreciate what this result is trying to say. So what this result is saying is that provided that a is a constant, so provided that the term in front of ln is a constant, when I differentiate, it's going to be a divided by u, so that comes from the standard result for the derivative of ln. So it's a divided by u multiplied by d by dx of the u term, and the u term is the term alongside the ln, okay, so to speak. So whatever u is, u comes from this term over here, okay, so that you take as u. So remember, dy over dx is a is a constant, so it's a over u. That is based on the standard result, but you need to multiply by d by dx of u, and u is the term alongside the ln, okay? However, if a is not a constant, we may need to use either the product or the quotient rule. So if a is not a constant, and if we got a product of two functions, then it's the product rule. And if a is not a constant again, and if we have a quotient of two functions, then we'll use the quotient rule. So let's try some examples. On the reverse. So example number 1. Let's underline this. So the question is to find dy by dx. Okay, so calculate dy over dx, or find dy over dx. And let's do a variety of problems. So in part A, let's have a look. Let's differentiate y is equal to 2 ln x squared plus x plus 1. So let's differentiate y is equal to 2 ln x squared plus x plus 1. Okay? First things first, let me look at the term in front of the ln. So the term in front of the ln is 2. So that is our a term. A is 2. 2 is indeed a constant, so we can use the chain rule related result. Okay? So remember, appreciate what the result is saying. So if you're differentiating a term of the form a ln ux, the result is a over u, so constant over u, times d by dx of u, and u is the term alongside the ln. Okay? So if we go back to this example, here is our u. So u is x squared plus x plus 1. So dy by dx, when we differentiate, it's going to be a is 2, divided by u is x squared plus x plus 1, multiplied by d by dx of u again, x squared plus x plus 1. And now it's just a matter of tidying this up. So d by dx of x squared plus x plus 1, that is 2x plus 1 if we differentiate this term. So if we simplify, 2 times 2x plus 1, let me leave this as 2 into 2x plus 1, divided by the x squared plus x plus 1. So this should be the solution to the first part, part A. Okay? So you only use the chain rule related result, remember, if the term in front of your function, which is ln, so the term in front of the ln function is a constant. So that is the reason why we use the chain rule related result. If it's not a constant, okay, it's either the product or quotient rule. Please bear that in mind. Let's try another one, part B. Let's differentiate y is equal to 1 over 2 ln sec 2x. So ln sec 2x is one term. So let's differentiate 1 over 2 ln sec 2x. So first things first, the term in front of ln is half. So that is our a term. Half is a constant. That means that we can use the chain rule related result. Okay? And remember what u is. U is sec 2x. So dy by dx. So let's calculate the derivative. So it's a divided by, so it's half divided by u, which is sec 2x, so it's a over u, multiplied by d by dx of u, u is sec 2x. Okay? Now it's a matter of tidying this up, so let's have a look. So the term in front of sec is 1. 1 is a constant, so we can use the chain rule related result for trigonometric functions. So if we differentiate sec, okay, the derivative of sec is sec tan, okay, so it's going to be a sec 2x tan 2x. So let's write that down. Sec 2x tan 2x multiplied by d by dx of the 2x. Okay? So if you're unfamiliar with the derivatives of trigonometric functions, be sure to watch the video. So I created a video which illustrates how you differentiate trigonometric functions. So if you haven't watched that video where I explain the derivatives of trigonometric functions, be sure to watch it. Okay? So back to the example, d by dx of 2x, that is simply 2. So in this case, dy by dx, let's tidy this up. I can cancel this 2 over here with this 2 on top, and I can also cancel the sec 2x here with the sec 2x on top to give me tan 2x. So that should be the solution to that part B. Let's try another one. Part C. Okay, let's differentiate y is equal to 4x squared ln sine 2x. So 4x squared ln sine 2x. So the term in front of ln, the function, is 4x squared. So that's our a, so to speak. Our term a is not a constant, it's a function of x. Okay, so that means that we're going to use product rule over here since we have a product of two functions. So I'm going to take that 4x squared term to be u, I'm going to take the remaining term to be v. Let's use the product rule. So step number 1, by product rule. So let me remind you of the rule. dy by dx, remember, for the product rule is v du over dx plus u dv over dx. Okay. Now in step number 2, let me do a side calculation, and let's calculate du over dx first. So u in this case is 4x squared. So that makes du by dx, when I differentiate, 8x. Okay? Alongside this side calculation, let's do another side calculation. So v is ln sine 2x. Let's work out dv over dx. So let's challenge ourselves. The term in front of ln, so our a term is 1. Okay, so that's the term in front of ln, 1. 1 is a constant, so we can use the chain rule related result. So in this case, it's going to be 1 over, now remember the u term is sine 2x. So it's 1 over u, which is sine 2x, times d by dx of the u term, which is sine 2x. Okay? So let's tidy this up. d by dx of sine 2x. So the term in front of sine is a constant, so we can use the chain rule related result for trigonometric functions. When I differentiate sine, it's cos, so it's a cos 2x times d by dx of the 2x term. Okay? So, further to that, d by dx of 2x is 2. So, dv over dx, when we simplify this, we're going to have a 2 cos 2x, so 2 cos 2x, divided by the sine 2x term here. Okay? And let me go one extra step. So dv over dx will be 2, and cos 2x divided by sine 2x is cot 2x. So that's the side calculation for dv over dx completed. Final step, step number 3. Let me replace these results here into our product rule. So dy by dx, that is equal to v. V is ln sine 2x. So ln sine 2x. Multiplied by du over dx, which is 8x. Plus u, so plus u is 4x squared, times dv over dx, which is 2 cot 2x. Okay, so let's tidy this up. So dy over dx will be, now I'm going to take out a common factor, so I have a 4 times 2, which is 8. I also have an 8 which is common over here also, so let me take out an 8 as a common factor. Also I have an x and an x squared term. Let me take out x as part of this common factor, so the overall common factor is 8x, and what is left within the brackets is ln sine 2x, okay, plus x cot 2x. So this is the term that remains by taking out a common factor of 8x. So this is the overall solution to part C. Okay. So remember, if the term in front of ln, the term in front of your function is not a constant, it's going to be either product or quotient rule. In this very example, we have a product of two functions. That is the very reason we're using the product rule. Okay. Right, let's try another example. So on the reverse. So example number 2. Let's take a red pen and a ruler, underline this. So the question is, find the equations of the tangent and normal to the curve, and the curve has equation y equals x ln x minus 2x at x is equal to 1. So let's find the equations of the tangent and normal to the curve y is equal to x ln x minus 2x at x equals 1. So remember, for the tangent and normal, we also need the y coordinate. So we just have the x coordinate here. We need the y coordinate firstly. So first and foremost, let me calculate that y coordinate. So at x equals 1, let me substitute x equals 1 into the equation. So I'll have y equals x, which is 1, ln x, which is 1, minus the 2 into x, which is 1. Okay. Now ln 1 is 0. So in this case, you're going to have 0 minus 2, which is minus 2. Okay. So that is the corresponding y coordinate for x equaling 1. Okay. Now for the tangent, we need dy over dx, so we need to differentiate. So first of all, we need to differentiate y to work out dy over dx. Okay, so y in this case is x ln x minus 2x. let's work out dy over dx. So we need dy over dx in particular to work out the gradient of the tangent. So I'm going to take u to be x, and I'm going to take v to be ln x. So let me write the product rule. So remember the rule, it's v. So, and let me do the calculation beneath. So my v is ln x multiplied by du over dx. So du over dx, and my u is x, so I want to differentiate x, it's 1, okay, plus u, so plus, and my u is x, times dv over dx. So my v is ln x, and I want to differentiate ln, that's the standard result, 1 over x, okay? So I've wrote down the product rule above in red, and I applied the product rule here to the function x ln x. And just to go back quickly, we're using a product rule because the term in front of our function is a function of x, okay? And also we have a product of two functions. So that's the product rule for x ln x minus, and when I differentiate 2x, simply 2, okay? Let's tidy this up. These two x's can cancel, so therefore dy by dx, so that's going to be ln x times 1, which is ln x, and 1 minus 2 is minus 1. So that's dy over dx, okay? Now, we have dy over dx, we need the gradient of the tangent. So for the gradient of the tangent, we're going to put the x value 1 into the derivative dy over dx. So gradient of the tangent. So I name the gradient of the tangent m1 when doing calculations involving tangents and normals. So m1 is the tangent gradient for me, and m2 is the normal gradient. So the gradient of the tangent to this curve m1, so if I replace the x value by 1, which is given, in dy over dx, we're going to have ln x, which is 1, minus the 1, ln 1 being 0, so the gradient of the tangent is minus 1, okay? So we have the gradient of the tangent, we have the x and y coordinates. Now we're ready to work out the equation of the tangent. So to calculate the equation of the tangent at the point x is 1, y is minus 2, we can use the formula y minus y1 is m into x minus x1, okay? So since the tangent is a straight line passing through the point 1 minus 2, we can apply this formula to work out the tangent equation. So the gradient here, m, is minus 1, that is the gradient of the tangent, and x1 and y1, the point that the tangent passes through, is having coordinates 1 and minus 2. So that's our data. So when we substitute the data in, we're going to have y minus y1, which is minus 2. That is equal to m is minus 1, into x minus x1, which is 1. So if I expand these brackets, I'll have y minus into a minus is plus 2. That's equal to, on the right hand side, minus 1 times x is minus x, minus 1 times minus 1 plus 1. So therefore, the equation of the tangent, if I take the plus 2 to the right hand side, I'll have minus x minus 1. So that should be the equation of the tangent, okay? So Now, we've got the equation of the tangent. Let's work out the equation of the normal. So before we work out the equation of the normal, we need the gradient of the normal. So first things first, gradient of the normal. Now, remember the theory of tangents and normals. The tangent and normal are perpendicular to one another. So if two lines are perpendicular, m1 times m2 equals -1. So in other words, the product of the gradients equal -1 if two lines are perpendicular. So let's use that result to work out. So let's use a fresh page. Let's use that result to work out the gradient of the normal. And I usually call my normal gradient m2. So since the tangent and normal are perpendicular, the product of the gradients m1 and m2 equate to -1. So m2, the gradient of our normal, is going to be -1 over m1 if I rearrange this. Okay? So m1 is our tangent gradient, and we had -1. Okay? So if I replace m1 in this rearranged result, m2 therefore is -1 over m1, which is -1, -1 over -1 plus 1. Okay? Now we have the gradient of the normal, and remember the theory about tangents and normals. The tangent and the normal pass through the same point. Same point implies x1 and y1. So they both pass through the point 1 minus 2. So bearing that in mind, let's work out the equation of the normal at the point 1 minus 2. So since the normal is a straight line, let's use the formula y minus y1, that is equal to m into x minus x1. So x1 and y1 are the coordinates 1 minus 2, and m is the gradient of the normal, which is 1 from our previous step. Okay? So if I substitute the data, I'll have y minus, y1 is -2, that is equal to m being 1 into x minus x1, which is 1. And if I simplify, I'll have y plus 2, so minus into -2 is plus 2 on the left. That is equal to 1 times x, which is x, 1 into -1, which is -1. And if I take that plus 2 over to the right hand side, y is equal to x minus 3. So that should be the equation of the normal. Okay? So that completes this example, example number 2, and these are the steps for that particular example. Okay? The important thing is, remember, if the term in front of your function is not a constant, so if it's a function of x, you may need to use either the product or the quotient rule. So once again, we had a product of two functions, so I applied the product rule here in this particular step to work out dy over dx. Okay? So that ends this video. I hope you found this video helpful. Okay, if you did enjoy the video, a like will be very much appreciated, and I hope to see you soon. Thank you.